Last time we started our discussion on one-dimensional quantum harmonic oscillator. So this is QM, one-dimensional harmonic oscillator. And we first estimated the energy and the size of this oscillator using the uncertainty principle. I'm just making a summary of the last time. With the uncertainty principle, we estimated the energy and the size of the oscillator. And we have seen that in that language, when you use uncertainty, there are two competing effects. And this is x prime, dimensionless distance. This was at 1. And harmonic oscillator is the balance between the restoring force, which is the harmonic attractive force, and the quantum pressure out, this one, due to the uncertainty principle. So it is the balance between the quantum pressure out and the restoring force, spring force, pulling it in. We have such examples, of course, using the uncertainty principle. One is the hydrogen atom, for example. We can say, following Professor Weisskopf, Victor Weisskopf, that the hydrogen atom is the balance between the quantum pressure out and the electrical Coulomb attraction in. So these two competing effects give the energy and give an estimate of the energy and the radius size of the hydrogen atom. There are other such examples. For example, sun is as a classical system, is the balance between the gravitational attraction and thermal pressure out. So atom will live in principle forever because uncertainty principle is there all the time providing this quantum pressure out. But the sun will die because the thermal pressure comes from burning of the hydrogen at the center, and finally when it depletes the hydrogen at the core, sun goes to another phase, a new equilibrium, burning heavier nuclei like helium. All right, then we discussed the Schrodinger equation for this harmonic oscillator, and we found out it again using dimensionless distance. This went as e to the minus x prime square over 2 times a polynomial, which by adjusting the term of the coefficient of x to the n in the polynomial to 2n is hn x prime. And of course you need to normalize this thing, but we did not compute the normalization coefficient, which we shall do today. So again, to remind you, this came about because of the behavior of psi for large x prime, and then we had a differential equation which we solved as a power series, but power series gave a two-term recursion relation, so we had an even series and an odd series, G even and G odd. And for the large values of the indices, remember this is G is AK x to the k. For large values of k, this had the tendency to go as e to the x squared, which of course x prime squared, which of course beats that asymptotic behavior. So we had to terminate the series. So you can terminate it either the even series or the odd series depending on the value of n, and then we keep one of them and put the other one to 0, providing this thing. And again, we will not use x prime anymore. I will just use x, noting that this is a dimensionless distance. And when we want to put the dimension back in, then explicitly we will say so and do so. Today, I want to focus on some properties of these Hermite polynomials to begin with, because they are very interesting functions of mathematical physics, and it also shows many techniques of special functions used in quantum physics or mathematical physics. And let us go back to the differential equation that the G had. This was so we will take it from here. G is G of x. Remember, we found, again, to repeat, the solution as power series, which we terminated. So G of x. It's interesting to look at its properties of these Hermite polynomials in the complex plane. So instead of x, let us use z, x plus iy. So d square dz square minus 2z d by dz plus 2n g of z is equal to 0. Or if we call this the differential operator L of z, g of z equals to 0. Now we can represent g of z as integral dt e to the zt vt. So it's a Laplace transform, but t is a complex variable. So we have a path going from A to B, and we don't know many things here. We don't know A, we don't know B, we don't know path C, and we don't know V of t. Okay, so let us apply this operator on this form. So Lg equals A to B dt c. These are derivatives with respect to z, so it's only working on this function. So this is t square minus 2z d by dz gives me a t plus 2n e to the zt v of t, and this is supposed to be 0. Now let us note z e to the zt, we can write it as d by dt e to the zt. If you take the derivative, z comes in. So I don't need this one anymore. T square plus 2n e to the zt v of t minus 2t v of t d by dt e to the zt. This is supposed to be 0. So we can use integration by parts. So it is, I'm just pulling this part, minus 2t v of t e to the zt d by dt minus e to the zt d by dt 2t v of t. Let's affect the derivative. Minus e to the zt parenthesis 2v plus 2t dv dt. So if I put that thing in, this is this part is just a can be integrated immediately. So let me write this part here. Lg is minus 2t v of t e to the zt. Just the surface terms. We evaluated, it does not depend on the path anymore, just these two. Then plus, let me erase this part. Plus a to b along the path c dt e to the zt t square plus 2n t square plus 2n v, and the sign here was minus, so this will become plus. E to the zt is out, plus 2v plus 2t dv dt plus 2t dv dt. So this whole thing is equal to 0. Now I can erase all this. Idea is the following. If v, right now we have a differential equation for v. If we set this, if we take v as that function that satisfies this differential equation, result is 0, and then we have to think about this a, b, and c. After finding v, we can discuss what the path should be, and what are the endpoints a, b. So let me write this again. Lg equals surface term. I will call this surface term. Plus, of course, we want the surface term to go away. A to b, c. dt e zt. Now I can write 2t d by dt plus t square plus 2n plus 2 equal to 0. So this is like another Alpar acting on V. So Lg is surface term plus dt e to the zt lv. This whole thing is equal to 0. So we choose v to be the solution of this equation. This Lg is supposed to be 0, so this whole thing is 0. This we will try to make 0. And if v satisfies Lv equals 0, then this term is gone. So we have found the solution of G as represented in the complex plane. So let us solve for v. 2t dv dt is equal to minus t square plus 2n plus 2v. We divide by v and we divide by 2t and multiply by dt. Okay. So if we integrate, log v equals, this is minus t over 2, so it is minus t squared over 4 plus, this is n plus 1 plus minus n plus 1 log t plus constant, which we don't care. If we exponentiate, v is equal to some constant times e to the minus t squared over 4 divided by t to the n plus 1. Because this is plus log 1 over t to the n plus 1. So we found v, and let's come back to the surface term. I am erasing this now. G of z, therefore, is some constant Cn a to b dt e to the zt minus t squared over 4 over t to the n plus 1. About some contour. Now we will decide on the contour and these endpoints. If we this has around t equals 0. This has no poles. This has a pole of n plus 1th order, and everybody is since n is an integer, this is also single valued. So if we just take an integral, for example, like this, this will be 0. So we have to take g will be 0. So we have to take something that is surrounding t equals 0. In that case, we take a equals to b somewhere on the thing. So a and b are the same points. So coming back to the surface term here, if a and b are the same points and v of t is single valued, so this thing vanishes. Okay. So surface term is 0. Term equals 0. Now, I'm erasing this part. So, and Cn is chosen to be 2n n factorial over 2 pi I. And ABC is simply an integral that surrounds the origin. That's it. So h and z, that we shall call now the Hermite polynomial of order n, is 2 to the n factorial over 2 pi I dt e to the zt minus t square over 4 over tn plus 1. Okay, so this is our Hermite polynomial as represented in the complex plane. So let us compute a few simple Hermite polynomials. In order to compute, we have to take the contour integral about point 0. And the way, rather than using complicated residue formulas, let's look at this. If you have 1 over 2 pi I dt over t is simply 1. So if there is a coefficient here, a, this is simply 1 times a equals a. Okay. So when we expand any other thing like 1 over t squared, 1 over t cubed, or t squared, or constant, they all give 0. The only thing is that the power should be 1 over t. So for low-lying things, let's just do simply. Let's take h0z is equal to 2 to the 0 factorial over 2 pi I and dt. Now n equals 0, this is 1 over t. So I am looking at the constant term in the expansion of this. So the constant term e to the x is 1 plus x squared over 2. So the only constant here is 1. So this is 1, 0 factorial is 1. This integral gives me 2 pi I, which knocks it down. So it is h0z is equal to 1. So let's write it someplace. h0z equals 1. Now the next one, I will erase. I will always use this. Let's do h1 and h2. It's enough, just to show you the technique. h1 of z is equal to 2 to the 1, 2. 1 factorial is 1 over 2 pi I dt. N equals 1, so I have t squared. I must look at the term that is linear in t. So I need t. So if you expand this thing, it is 1 plus e to the 1 plus zt minus t square over 4 plus the square of it, etc. But the only linear term is this one, t, and the coefficient is just z. So this is like 1 over t, so this gives me 2 pi I. This knocks it off, so it is 2z. So h1z is equal to 2z. Let's look at h2. h2z is equal to 2 factorial, another 2, over 2 pi I dt. This is now t cubed, n equals to t cubed. So I must look at the coefficient of t square. because t squared over 3 cubed goes as 1 over t, and all I need the coefficient in terms of here. So let's expand it again. 1 plus zt minus t squared over 4 plus 1 half zt minus t squared over 4 square. So t squared terms are, I have a minus 1 over 4 from here, minus 1 over 4. And when you square it, I have a z square, then you divide by 2, plus z square over 2. This gives 2 pi I, which knocks this down. So it is 8 times 4, 8. 8 times minus 1 over 4 plus z square over 2, which is 4z square minus 2. So h2z is equal to 4z square minus 2. Of course, we can continue, we can write general formulas for general h and z, but that's not needed, okay? All right, so I'm erasing this part. So the integral representation of the Hermite polynomial is ideal to derive a generating function for the Hermite polynomials. Let us construct, for example, sum over n from 0 to infinity, h to the n, h and z over n factorial. And let us call this the generating function hz. This is equal to sum over n, h to the n over n factorial times 2 to the n factorial over 2 pi I dt e to the zt minus t square over 4 over tn plus 1. So I have an integral, and then I have a summation over that integral. If I interchange summation and integral, so that I do the n sum first. So dt e to the zt minus t square over 4 divided by factor t here. And then n factorials cancelled here, and 1 over 2 pi I is here. Sum over n, 2 to the n, h to the n, and t to the n. H is goes from 0 to infinity, and h is a small parameter, so that we can say this is 1 over 1 minus 2h over t. So when you multiply it by t, this becomes 1 over 2 pi I dt e to the zt minus t square over 4 over t minus 2h. So the pole after the summation is at t equals 2h. And it's a simple pole because these are regular there. So the result is 2 pi I times when replacing t by 2h. So it is e to the 2h z minus 4h square over 4. That's it. So GHZ GZH is equal to, I changed the order, doesn't matter, e to the 2zh minus h square. Which is just, let me just write again, sum over n, h to the n, h n z over n factorial. So it's an incredible summation. All these complicated hns up to infinity, they can be summed and to this generating function. All right, we take a short break. All right, we will now derive some properties of the Hermite polynomials using the generating functions. Let me just now change complex z to real. Okay. First, we note that, let me just erase this a bit better. G of minus xh, if you make it minus xh, it is the same thing as g of x minus h. So let us use the definitions. N, h to the n, hn minus x over n factorial, that's equal to n minus h to the n, hn x over n factorial. Now let us compare the the coefficients in terms of hn. We see that hn minus x is equal to minus to the n hn x. So for n even, these functions, which were defined like this or like that, are even, and if n is odd, it is odd. So h and even is even, h and odd is odd. So this is the symmetry of these functions. 2, all right, let me just write it here and get rid of the hn minus x is equal to minus n hn x. Let me just erase. This is now 2. Let us consider, for example, delta g, delta x. This is 2h g, which is sum over n. Now I am using this part, taking the derivative, only takes the derivative of this. So hn prime x over n factorial. Let's look at here. I will expand this like that and compare the coefficients in terms of h to the n. So it is sum over n, 2 hn plus 1 hn divided by n factorial. That's equal to n hn prime x over n factorial. So this goes as hn plus 1. So let's make this n plus 1. I'm looking at the coefficients of hn plus 1. They have to be equal. So 2 hn over n factorial must be equal to hn plus 1. So n plus 1 over n plus 1 factorial. This is n plus 1 times n factorial. So these cancel. So h prime n plus 1 is equal to 2n plus 2 hn. Let me write it here. hn plus 1 prime is equal to 2n plus 2 hn. I will erase the computational part. Three delta h gxh is equal to this is 2x minus 2h gxh and for 2h we can write 2x minus d by dx gxh. If you write the series form, this is n h n minus 1 hn divided by n factorial is equal to, we write the expansion, this form again. This is equal to hn over n factorial 2x hn minus hn prime. So let us compare the powers of h to the n. So this is n minus 1 factorial. So compare to the powers of hn. From here we have hn plus 1, because n plus 1 minus 1 is h to the n, divided by n factorial. That's equal to 2x minus 2x hn minus hn prime over n factorial. So n factorial is cancelled. We have another recursion relation. hn plus 1 equals 2x hn minus hn prime. I will erase this part. These, of course, are so-called the recursion relations. Recursion relations. RR. For example, let us take this one. It says that if you know Hn, then you know its derivative, and you can construct Hn plus 1. Let us do a few simple ones. H0x is equal to 1. Therefore, H1 of x is equal to 2x H0 minus H0 prime derivative, that's 0. This is 1, so it is equal to 2x. Let's do one more. H2 of x, second polynomial, 2x times H1 minus H1 prime. H1 is 2x, so it is 4x squared. And derivative is 2 minus 2. So this is another way of. Remember, we obtained the infinite, we cut the infinite series, and we said we can, the coefficient of the greatest power x to the n will be 2 to the n. Then we constructed the Hermite polynomials. Second, we constructed Hermite polynomials using their integral representation in the complex plane. This is the third time we can use recursion relations to construct these Hermite polynomials. All right. So what else we can do? I'm erasing this part, that we can generate the higher Hermite polynomials if we know the lower ones. It's gone. Let us take the derivative of this one. Take d by dx. We take the derivative of this relation, hn plus 1 prime is equal to the derivative of this thing, 2hn plus 2x hn prime minus hn double. But from here, this is also equal to, from the first recursion relation, 2n hn plus 2hn equals. So this knocks it off. If we carry these things over, hn double minus 2x hn prime plus 2n hn is equal to 0. That's our original equation. Dx squared minus 2x d by dx plus 2n hn is equal to 0. So it's like completing the circuit. We started from the differential equation. We went to for the Hermite polynomials, we went to the integral representation in the complex plane. Then we constructed the generating function. Then we constructed the recursion relations. Then we went back to the differential equation. So we could start from any point. If we start from here, given the recursion relations, we can obtain the differential equation, given the integral representation. So you can take any of these things as the starting point and the definition of Hermite polynomials. There is one more interesting relation we can derive. I'm erasing this part. From the form of the generating function, we observe that delta n g delta h n. If you take the n derivatives, this brings n factorial, and if you put h equals 0 afterwards, this kills all the higher powers higher than h. This is simply h and x. Let us multiply both sides by e to the minus x square. And since x is not under the operation of derivative with respect to h, we can bring it inside. So it is del h n g times e to the minus x squared. Then you put h equals 0. As far as h operation is concerned, this is just like a constant. And now let us write the form of the compact form of the generating function, delta n, delta h n. This is e to the 2x h minus h square. And now we multiply by e to the minus x square. Then we put h equals 0. But what is this? This is e to the minus x minus h square. Minus x square, minus h square, minus 2xh, minus x plus 2xh. Now this is a function of x minus h. Therefore, derivative with respect to h can be converted to a derivative which is onto x, but with a minus sign. Since we are taking the derivative n times, so this is minus d by dx to the n, e to the minus x minus h square, and we set h equals 0. We can set h equals 0 immediately. So it is minus to the n. I can just use d by dx because there is no h anymore. D by dx to the n, e to the minus x square. And what is this equal to? This is equal to h and e to the minus x square. Therefore, another expression for hn is, just bring it to the right, e to the minus to the n, e to the x square, d by dx to the n, e to the minus x square. So this is called the Rodriguez formula. Rodriguez formula. It's not so easy in practice for larger n because every time you differentiate with respect to x, you bring a power of x, and then next time you differentiate not only that, but also the polynomial that is collecting in front. However, it's a very compact and nice relation for Hermite polynomials. All right, we now came to the last point of this lecture because it is the normalization integral. So I am erasing all this. Remember, we obtained psi n of x prime as some normalization coefficient, which we don't know yet, e to the minus, I will just use x, e to the minus x square over 2, and hn x. This is a dimensionless x. So we would like to learn about this integral j n m is equal to nn dx minus infinity to plus infinity e to the minus x square times hnx. So let's call it INM. That's equal to NN INM. So we would like to take this integral for arbitrary n and for arbitrary m. To take it general is quite difficult, and that's not what one does. Better is to use to get the help from the generating functions. So instead we consider this. We consider minus infinity to plus infinity dx e to the minus x square times gxh and gxt equals. Now we write their forms. Sum over n and m, h to the n, t to the m over n factorial, m factorial. And the rest of the integral is I and m. The question is, can we take the left integral? It turns out this is an easy integral. This is dx e to the minus x square. Let us write this. E to the 2xh minus h square e to the 2xt minus t square. And let's look at how does it look. We have x square, h square, t square. We have 2xh and 2xt. Let us complete the square. So we multiply by e to the minus 2 ht and e to the 2ht. So this part will collect as e to the minus x minus h minus t square. Let's check. We have the squares with a minus sign, okay. Plus 2xh, it is here. Plus 2xt, it is here. Then this is plus and minus. Minus is there, so 2ht is out. Okay. And this is dx. This is simply a Gaussian integral. Just change the x to x minus h minus t. So the result is root pi. So this integral is root pi times e to the 2ht. So 2 to the n, h to the n, t to the n over n factorial. And we compare it with this form. First, what do we see? No terms on the right such that h, the power of h and power of t are different. They occur in the form ht to the n. So first of all, I and m must be proportional to delta nm. Otherwise, it is 0. Suppose it is indices are equal, then I have h to the n, t to the n over n factorial I n n equals root pi 2 to the n, h to the n, t to the n over n factorial. So n factorials cancel. H and tn goes away. So I n n is equal to root pi 2 to the n, n factorial. I will erase this one. So JNN will be NN square. We can make it absolute square, but everything is real, so it doesn't matter. NN is equal to INN. And we want this to be 1. So this is NN square root pi 2 to the n factorial is equal to 1. Therefore, NN is equal to 1 over pi 1 over 4 root 2 to the n factorial. So finally, we have the normalized wave function. I can erase this part now. Psi n. Now I will use x prime. X prime dimensionless. X prime dimensionless. Okay, sin x prime is 1 over pi 1 over 4 1 over root 2 to the n factorial e to the minus x prime square over 2 h n x prime. Finally, this is the we can also represent it as x prime n. I'm erasing this part. Finally, this is the normalized wave function. And I think everybody should remember the ground state of the harmonic oscillator, which is the n equals 0. Psi 0 x prime is equal to 1 over pi 1 over 4. This is total 0, 1. Simply e to the minus x prime square over 2, and h0 x prime is just 1. So this is the ground state, the lowest state. Ground state, this is the nth state, and the energy goes as E and E prime, and is simply n plus half. This is in units of h bar omega, so the real energy is h bar omega times that. Now, what about, we are basically finished. But what about, let me just do that also. What if you want to write it in terms of x, the real position, okay? So, if we will write psi n of x prime will be some constant times psi n x. Remember, x was equal to h bar m omega x prime. Okay, so that's the length times x prime, and this is dimensionless. So dx prime psi n x prime square is equal to 1. Psi n x prime is c squared psi n x. C square. Dx prime is root m omega over h prime dx psi n x square. This is equal to 1. So this is the normalized state. Therefore, 1 over c is m omega over h bar 1 over 4. And psi n x is equal to 1 over c psi n of x prime and 1 over c is here. So we just put it n omega over pi h bar 1 over 4, 1 over root 2 to the n factorial, e to the minus x prime square is m omega over h bar, m omega x square over 2h bar, and hn root m omega over h bar x. So here x is the actual distance. This is the dimensionless. But this also gives a good indication on the advantage of using dimensionless variables. It is so simple compared to this form. So one should use this one, and at the very end, if needed, you can put the constants back to make things dimensional. All right. So in summary, we started from the differential. Let me just summarize. We started from the differential equation. We went to the integral representation. We went to the generating function, recursion relations, and back to differential equation again. And using the generating function, we showed that these wave functions are orthonormal with this normalization constant. So it was a good exercise, if you wish, about the properties of the Hermite polynomials. Now, next time, I want to say something about the next time. One-dimensional harmonic oscillator problem admits nice algebraic representation, and we will look at it next time. Thank you.